అందరికీ నమస్కారములు. సర్వేభ్యో నమో నమః. నమస్కారః. Today is the second day of our classes on Vedic mathematics by Dr. Goutham Mukherjee ji. We have 5 classes on this. Today is the second class. Yesterday we had one. We will start the session with reciting Vande Mataram and paying our respects to our country, and then after that Prarthana. So let us request Srinivas Garu to recite Vande Mataram, please.
Vande Mataram, Vande Mataram, Sujalam, Sufalam, Malayaja Sitalam, Tasya Shamalam, Mataram, Vande Mataram. Subhrajyosna pulakitayamini pullakusumita drumadala sobhini suhasini sumadhara bhashini sukhadam varadam mataram Vande Mataram Vande Mataram
వందే మాతరం. ధన్యవాదములండి శ్రీనివాస్ గారు. Now
Namaskaram.
let us request Vasundhara ji to chant Prarthana, please.
Sarvebhyah namaskara. 1 minute meditation followed by 3 times Omkar. Omkar. Om Ganana Tva Ganapati Hawamahe Kavim Kavinamupamasthamastamam Jeshtarajam Brahmanan Brahmanaspata Anashunvannoti Bhisidhasadanam. Om Shri Mahaganadhipataye Namaha. Om Prano Devi Saraswati Vajebhirvajinivati Dhinama Vitriyavatu. Om Shri Mahasaraswatyai Namaha. Gurureva Gati Gurureva Bhaje Gurunaiva Sahasmi Namo Gurave Na Guruh Paramam Susurasmi Guroh मतिरस्ति गुरौ मां पाहि गुरौ ज्ञानानन्दमयं देवं निर्मलस्फटिकाकृतिम् आधारं सर्वविद्यानां हयग्रीवमुपास्महे श्रुतिस्मृतिपुराणानाम् आलयं करुणालयं नमामि भगवत्पाद शङ्करं लोकशङ्करं शङ्करं शङ्कराचार्यं केशवं बादरायणं सूत्रभाष्यकृतौ वन्दे भगवन्तौ पुनः पुनः ईश्वरो गुरुरात्मेति मूर्तिभेदविभागिने व्योमवद्व्याप्तदेहाय दक्षिणामूर्तये नमः असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्योर्मा अमृतङ्गमय ॐ शान्ति शान्ति शान्तिः मातृदेवो भव पितृदेवो भव आचार्यदेवो भव अतिथिदेवो भव ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः
గురుభ్యో నమః.
గురుభ్యో
హరి ఓం.
నమః.
ధన్యవాదములండి వసుంధరా గారు. థ్యాంక్ యూ సో మచ్. Now let us request our Guruji, Goutham Mukherjee ji, to start the webinar, please. I think you have to unmute or what? Please unmute yourself. Yeah.
Can you see the screen, please?
Yeah, we can see the screen.
So yesterday we covered up to this point, and we explained also partly about this coming of half here. Actually, half at a particular position means, say, half in 100 means half of 100. That means 50 in the tens position. That we did here 6, and then it became, when we add this 50 with 160, it becomes 210. So that's how this is written like this, and these two finally added to 6. So this becomes 8 and 10. So 810 becomes the answer. So, and we also explained the algebra behind doing sub-base with the base. Today we will do start another new topic. It is the Tirjak method, Urdhva Tirjakabhyam method of the multiplication, general multiplication. Am I audible in this voice, level
Yes.
of voice?
Yes, yes.
Now,
Hmm.
it is a slightly different than the way we do multiplication in since school days we learned multiplication. Like here, we would multiply 5 with the top one first, and then again the next line we multiply 2 with the whole top of the thing and shift it towards left. So, but here the algebra is different. There the algebra was different. It is multiplying fully with a particular digit of the lower number, lower multiplicand. Here actually we are grouping them into units, tens, and hundreds coming out of the expression like this. So if this can be, this is say A is 4 here and B is 3 here, and C is 2 here and D is 5 here. So if you, this is so 43 is basically 10A plus B, and 25 is basically 10C plus D. So what we do, we group into this, and so that this A and C will be multiplied here, 4 and 8. Here A and D means that 4 with 5 and 3 with 2 will be multiplied and added. And then in the leftmost, actually, unit digit, this unit of this one will be multiplied with the unit of this one. So like I have shown here through arrows. So it is actually, so this is called urdhva, or here downwards, but actually it's called urdhva, and the tirjak. This is tirjak. So now what we do? So we can multiply 4, we can do it any sequence, either left to right or right to left, doesn't matter. 4 into 2 is 8. Okay, I put it here. And then 4 into 5, 20, plus this 3 into 2 is 6, 26. 26, we write 6 here and 2 below 8. Basically, it is actually coming to higher higher place value position. And then 3 into 5 is 15. Again, there is a carry. So again, 5 is here. And 1 we write with a higher place value below 6. Okay. So then finally we add it. So it becomes 1075. This is the answer. Is it clear? I come to another higher one. So 3 digits. 3 digits also, you express these 3 digits. If we express it like this, you don't have to do this. Is not part of the procedure. This is to just explain the algebra. Like this, 3 into 3 is 9. And again, 3 into 5 plus 1 into 3, it is 15 plus
Please unmute yourself.
do you hear me?
Now we hear you.
So some network problem happened or what? I don't know from my side or.
You have come out of the sharing.
Oh. Achha, up to where I was audible. I was explaining this one. 3 into 3 is 9.
Yes.
So 3 into 5 plus 1 into 3 is 18, and then 88 right here, 1 below 9, because a higher place value. Then 3 into 2 plus 4 into 3 is 18, plus this 5 into 1, 23, 3 here and 2 here. 23, so this 23, 2 of 23 is actually higher place value. So we write is carry basically. Then 1 into 2 plus 4 into 5 is 22, 2 here and 2 here, below this 3. And then 4 into 2 is 8, like this. So this finally we add, and then we get the result. So is the procedure understandable? Here, if is any reaction? Basically, we are doing multiplication, but with a different grouping. And it is found that while it is translated into computer circuits, this becomes more efficient. And as a result, it can save a lot of power. It can be proved. That one paper I have seen, and that it argued that by doing so, there are trillions of different devices, and each devices involve a lot of multiplications. So if this multiplication method is used, then it can save power of the order of megawatts. So it is like this. We come to higher value here. Now this is the 5-digit. So I have explained here actually leftmost digit is 2 into 3 is 6 into is equal to 6. The leftward one is 2 into 5 plus 3 into 3 is 19. 9 here and 1 here. Middle actually 2 into 2. Middle one is actually 2 into 2 plus 1 into 3 is 3 into 4. This one actually. Here to do actually like this one. I'll tell you. Middle one is like this. 2 goes to 2, 1 goes to 3. This 3 is to 4. This 3 is 5, and 4 into 6. This is the middle term. This one. Okay. So it is a matter of practice, understanding that how it is happening. Like this one actually, before that, this digit, this will be this one, this one, this one, and this one. Always it will be symmetric. Find it, wherever you take, first you take this one. Only 2 and 3. So it is straight. Okay. Next you are taking, we're considering this 2 with 2. So this also becomes symmetric out of this. Okay. Then you are coming, considering 3 with this, total 3. Here also it is symmetric like this, this, and this. That is, you are gradually developing from left side, and then you are considering 4. You always see that when it is 5, you consider 1, then 2, then 3, 4. This I am shown 4, then 5, and again the other side 4, 3, 2, and finally 1. That is the idea. Now here this is 4 I am considering. So here also it is symmetric like this. This into this plus this into this plus this into this plus this into this. So basically, initially it may look very complicated compared to your earlier, but remember here 5 into 5 will mean 5 lines. Here just it came to into 2 lines. So 5 into 5 will mean 5 lines like this. Instead of that, by this operation, you are compressing these into 2 lines only. One for this one, another for carry. Carry maybe sometimes 100 digits may also come sometimes. Now, again, I am coming to the total 5. The whole thing is 5. Now, again, we do symmetric like this, 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 and this. Then again I come to the second, the left side 4. On 5, we can reduce to 4 in this one. Okay. Then I come to 3. Considering these 3, the last 3. This and this. These are all written here. Then come to 2. This 2. This into this plus this into this. And finally 1. The 1 into. See, 1 into 2 is here. 3 into 2 plus 1 into 4 is 10. So 1 is 0, 1 is 10. Then here 4 into 2 plus 1 into 6 plus 3 into 4 was 26. 6 is here and 2 is here. Like this. You'll find all these numbers here. This leftmost is 2 into 3 is 6. 6 is there, 6, 19, 39, 55. 55 is the middle one is actually 58, the highest one. Then here 45, then 26, 10, and 2. These numbers are written like this, and then finally added, and it becomes in the result. Although it looks complicated, because but by practice it will be easier. You'll find it. Sometimes you do, maybe you can do it in memory. With practice, it can done in memory, but otherwise also you can write like this somewhere, and then you can write them. Is the procedure clear? Any answer?
Sir?
Yeah.
Sir, here, when we are trying to multiply 5 by 5, like 5 digits by 5, we'll get 10 digits, huh? Like 10 digits will have an answer, huh?
That depends actually. Not always, because
I think if you have higher numbers,
if
maybe 10.
the leftmost becomes 2 digit, okay, then only it will become 10 digits. Otherwise, it is 9 digits. It can happen with 9 digits.
Sir, in the first line you said leftmost digit 2 into 3, 6, and again we went to 2 into 5 and 3 into 3. Again we went into 2 into, directly it should go to 2 into 6, no? You went to 2 into 4 in the next one.
Next one?
Next, 2 into 6 plus 3 into 5 plus 4 into 3. Okay.
2 into 6, 3 into 4 plus 3 into 5 and 3 into 4 into 3. Yes, right.
Again, we went to 2 into 4. Okay.
Like whatever you do, first you consider only 1, then you consider next 2, next you consider 3, then you consider 4, then you, this is 5 digits into 5 digits, so you consider 5. Then again you do 4, second one, this side 4. Then again,
okay.
Then 2, and finally 1 unit digit 1. Now, if it becomes equal, suppose had it been only 5, 6, 4, 2, what you do? You put a consider it 0 here.
Okay, that's way, yeah, fine.
That way you match this thing, and then you can do. Whatever you in the left you pad up with 0, the other one, smaller one, and then you make them equal, and then you can do that. Okay.
So here the leftmost digit will become 0. Like in the 2 into 3, we got 6.
Yeah,
if we give 0 there,
it will start with 2. It will start with 2 into 3 into 3 plus 3 into 0 means 2 into 5, 10. It will start with 10, so it will be 10 like this. This will not be there, and this will be starting with 10. And everything, of course, will be changed because this part will not be there. Okay.
Okay. Thank you.
So now, any more question?
Sir, if the digits are actually one is odd number and the other one is even number. Suppose in the first figure we have 5 and the other one 6 digits. Multiplication, same rule we have to follow, or
Then suppose had it been say another.
you have given both the sides actually 5 digits.
Okay, suppose it is 6 digits. As I told, this you pad up with 0. Make them equal. Then you do it.
Okay, understood.
So now next slide we had some comparison, general multiplication with the two-jug method, and here actually same example. Yes, same example. What I did, I wrote in a different thing.
Welcome.
In a sparse formation, so that it becomes very clear actually. So this is below this one. This is totally below this one. this into this plus this into this is below this one actually, comes like this. This into this plus this into this into this is below this one. This into this into this thing is below this one. So that way it is sparse method, so it becomes very clear. You can at laser you can see it. Now I did a additional thing, one additional thing, which is something is some digits are more than 5. So why 5 also is involved like this? If you say 5, if you express this 56 as a vinculum number to reduce this more than 5, it becomes 6 and 4. Okay. So it cannot again becomes 5 becomes 6. So it can becomes more than 5. So it was 356. So it finally did 4 and 4 and 4 we are on the vinculum. So that is the idea where I sometimes told that greater than equal to 5. Because single 5, it will not happen. Anything will not happen. You can keep it. But when after 5 there is a more than 5 is there, it will make this 5 as it will increase the 5 to 6. Okay. So that's what I told, that sometimes 5 also have to be converted. So like this. So with this one, you see that so many carries were there here. There are so many carries, but here only 2 carries we. So 3 into 2 plus 1 into 4. 2 into 1 plus this one. So 3 into 2 plus 1 is 10. Here 10. Then 4 into 2 minus 4 into 1 becomes 4, and plus 3 into 4 is 12, 16. It becomes 16. And then we'll find that 3 into 2 plus 1 into minus 4 means that it becomes 2. 2 and 16 and this 12. Again 4. 2 plus 4 is 6. Only 6 came here. Okay. That way, if there are some negative vinculums, they becomes, and these also became to negative. And then finally, you this Nikilam Navadastaram, so you see here equilibrium, and then this is Nikilam Navatar from 9, and this is from 10. So this becomes 3, 5, 1, this part. 4 and 4, 8, 8 becomes 3, 5, 1, 2, and we get the answer. So you can use the vinculum. Now I come to, is this clear? The application of vinculum in this? You have to consider the sign. While multiplying with negative numbers, when vinculum is negative, so you have to consider the sign always. That sign you have to add it accordingly. Should I slightly elaborate it here? Should I?
Yes, sir. Vinculum, could you elaborate?
This, suppose I consider this part. Okay, that in the state. Now, how it came here? You will tell me. Please tell me. 3 into what? 3 into 2. Okay. 6. Then 4 into 4. 16. Three into 2, 4 into 4. Then 3 into minus 4. Minus 4 is minus 12.
Minus 12.
Minus 12. And 3 into and minus 4 into 1. Minus 4 into 1 is equal to minus 4. Minus 4. So how much it becomes? Here 2 and here 4. It becomes, the real becomes 6. So this part is 6. This 6. This is coming as 6. No carry. See, there is no carry there. So that is the idea where negative numbers, vinculums can reduce our effort. So you have to be conversant with using positive and negative numbers both, and so that it becomes more flexible. Although it's not adding, but sometimes it may be subtracting also. So this is clear.
Acharya,
Uh,
can you please explain the reasoning behind becoming 5 and 6 becoming -4 once again?
which one? Oh, acha, 350. 356. Yeah,
Yes.
356. I told you that if I this 56, if I write 6 and 55 into 10 plus 6 is equal to 6 into 10 minus 4. Okay. Suppose I want to instead of 6, I want to convert it into vinculum. Then actually it will increase it to 6. So instead of that, what I'm doing, because it is 56, so what you can do, it is actually 400 minus 44, isn't it? 356, that is 400 minus 44. This becomes 4 and 4 vinculum, 4 vinculum, 44 vinculum. This can write in separate also, or you can join them like this. Both are same. Meaning of both are become same. Is it clear? Is it clear?
Not exactly, Acharya. I didn't properly understand.
If you do not get it, you will consider this two part like this. I'll tell you as I shown you.
356, 64.
Yeah. First you do it like this. I erase it. Yeah. First you consider that 356 was there. Okay. So you
Okay.
consider it to be 3 and 6, 4. 5, 6 becomes 6 and 4 vinculum. Now forget it. And 3, 6, it becomes 4 and 4. This part becomes this part. Okay. This comes to this. Now this part you consider. Only this part. This came to this. Then you 2 steps you consider. This is also another way. Is it clear now?
Guruji, namaste.
Namaste.
No. 356 is near to 500, no? You have to take 500. Why you are taking 400, sir?
Oh no. That is nothing to that is nothing to do with that that method of multiplication. Here I am expressing it in vinculum only. That is that much that only that much part. I am not multiplying something with this. That is not that multiplication method.
Okay, sir.
I'm just expressing it. I'm not doing any multiplication. Here I'm this 356. I consider into express it into vinculum method, vinculum notation. Okay. Okay. Should I come to the next slide?
Yes, Acharya.
Yeah. Now comparison between multiplication methods. Now there is a suppose I've chosen especially these big numbers. Now Urdhva Tujya, this one, you'll find that lot many it will leave lot many actually carries even in the order of 100. Okay. So in order to get rid of these, we express it in vinculum. 889 becomes 1 and 111. Because 8 itself is also more than 5. So if we do like this, see, suppose had it been 0. So this 0 is increased to 1. Then this Nikilam Navatas Charamang Dasata. 9 minus 8, 9 minus 8, 10 minus 9, or becomes 1, 1, and 1. 8, 9, 8. So this also becomes 0 becomes 1, and then 8 and 9 becomes vinculum 1 and 0. 9 minus 9 is 0. And then 10 minus 8 is 2 vinculum. Now, if we consider this Urdhva 1 into 2, this 1 vinculum into 2 vinculum is positive 2. Then 1 into this minus 1 into minus 2 plus this one, it also becomes 2. Then what this one into this one plus this one into this one plus this one becomes 3. Okay. Because it is 0. Then it becomes 1 into 2 minus 2. This becomes minus 2, and then this becomes minus 1 minus 3, and then it becomes this becomes 0 and 1 is 1. So it becomes minus 2. That way it goes like it will go like this, and then actually it becomes, here the vinculum 202, 1 and 202, 1 becomes 0, and this 202 is total vinculum actually here. 0 actually doesn't matter. So here actually 9 minus 2 is 7, 9 minus 0 is 9, and 10 minus 2 is 8. So 798, and then 322 remains like this one, this question. Through Nichilam Navadas Charamang Dashattu method, what we did here, actually 889 will express as, because the base is 10,000. Base is 1000 here. So it becomes minus 111, and this becomes minus 102. It will be similar to this one. Now 889 minus 300, 889 minus 102 becomes 787, or something as 898 minus 111, 787. Now this becomes, multiplication of this is 11322. How? Now again I can do it separately. 111 into 102, it is here the base is again 1000. So it is base is 100. The base is 100. Base is 100. It is near 100, no? 100, and then it becomes plus 11. This becomes plus 02. Okay? This becomes 22, and this becomes 111 plus 2 is 113. So since here it cannot fit here, because it is only 10, the 3 digits are kept here because the 3 zeros are there. So we have to put it as a carry and finally add it here. So 322 becomes, and this becomes added to this 709. This becomes the answer. Now we consider conventional method. So this we have shown it Urdhva Trijagabham, and this is Nichilam Navadas. Same problem, we do it our conventional method. So 8 into this one, it becomes 7, 1, 1, 2. If we multiply with 8, everything is multiplied by 9, becomes this one. Again, you multiply with 8, it becomes this, and finally you add. This is our conventional method. Since school, we have learned this. And conventional method, but using vinculum. So we convert it into vinculum. Then if we do like this, minus 2, everything we write, it becomes like this. 0, of course, it is not there. So therefore, I shifted to that line I did, total line I didn't write. 0, 0, it was 0, 0, 0, 0. Because everything is multiplying with 0, multiplied by 0. So this minus 1 multiplied with only sign change. And then 1 with this one becomes like this. And when you add, it becomes like this. And then if you convert it into this one, it becomes converted. Vinculum is converted to this one, Nichilam Navadas, etc. It becomes like this. So you tell me which one is easiest here? Urdhva Trijagabham or Nichilam Navadas, or your conventional method or conventional method with vinculum. You tell me. Your answer may vary, of course. Some person may think that this is the easier. Sometimes some person may think that this is easiest. You tell me which is easiest. So that what I meant to say is that
Conventional method is easy.
which one? This one,
Conventional.
no? Huh?
No,
Nikilam Navataha.
Nikilam Navatas. Directly you are getting the answer. See, so quickly you are getting answer here. 2 steps are there, of course, given that problem. Plus, somebody told that conventional method is the easiest one because you have a lot of practice, or what?
no, sir, it is easy to understand. That's why.
Easy to understand because since childhood you did it, so therefore it looks easy to understand.
Maybe.
That is the thing. So therefore I told that actually from school level itself there should be these alternatives. People should keep grow with these all alternatives together. So they do not have bias on a particular method, and depending upon the situation they can apply the best one. Here actually as you told, this Nikilam Navatasana looks much better, easiest compared to others. This also is good. Some are in this Vinkulam. Even using Vinkulam, this also looks good. Using Vinkulam, this also is quite good. No problem with this. But of course, this is the very cumbersome. Always you have to remember the tables of 8, 9, and so on. So this is actually this. So that is the idea of comparison between these things. So comparison between the multiplication algebra, the 3-digit number with 3-digit number. A conventional method we do like this. Everything we multiply with the left. This is the suppose this is the rightmost digit. Next digit 10, 100 and 10. Sorry, unit 10, 100. So everything is multiplied by this, and then everything is multiplied by this one. Everything is multiplied by this 3rd digit. Okay. Then you shift it. Shift means actually multiplied by 10, 100 and so on. Then added. However, Urdhva we have already shown. They are grouped actually. Grouped into unit, 10, 100, 1000 and 10,000. Okay. So that way.
Sir, if we have a number of 5, 6, 7, 8 and number of 3, 2, and like multiply by 3, 2, can this method can be applicable? Like 2,
Yeah, they
4
told
digits and
you have to pad up by pad up from the left to zeros to make them equal. Why not? It can be done.
We need to say 5, 6, 7, 8, 52 I want to multiply, then I need to have 2 zeros, then 5, 2.
Yeah.
Okay.
So that 2 zeros are padded to show you that actually in this the grouping should be proper. So to have the proper grouping, you should have idea that what to be multiplied with what, isn't it? So
Okay.
that if you place it in a wrong position, then you may multiply wrong thing with wrong thing. It will not come. It should be in the same sequence. Okay. So that is that is why to pad up with zeros.
Why I asked, because vermicula 52, then you need to have vermicula of 52 also, right? That's why I asked you, because 100 in the place of 52, we'll have a vermicula, we'll use 100, right?
There is 0 in 100, yes.
Yeah, okay. Okay, fine. I'll try it and again ask you tomorrow.
Okay. Yes, you try? Yeah. So some homeworks are given here. You have to find the method properly. Choose the best multiplication method and evaluate. Even may compare more than one method and comment. So here actually I have given some this one. This you can easily look at now which method should be best. So you can find that which method, and sometimes with vinculam, without vinculam, this you can use. This you can no. What is the best method for this one? Can you tell me? Are you remembering the method actually? Name of the method? Like yesterday we discussed about what method? What is called that one? And today we started with what method? What is the name?
Conventional method.
No.
Today it's Tiryag method, sir.
Urdu Trijagabham. And yesterday's method was called?
Nikilam Navta.
Exactly. Nikilam Namatas Sarvanta. So this is the method. And so basically, when it's near about a base, we are considering is by Nikilam Namatas Sarvanta. So we are basically subtracting it from the nearest, subtracting or adding to nearest base. And then we are doing it and cross subtraction or cross addition, as the case may be, and then we are doing shifting towards this. So multiplication method, you just, these are the homeworks you please do, and as it is written here, and because it is it is shared actually, no, this whole presentation is shared. Please go through them and find this one, find these products and do it. Okay, it is all given to you. Now today, because time is actually only 5 days and there are so many topics, so I start with, I may not complete it today, start with the division by Nikilam method. So any remaining questions are there from the whole multiplication methods? Maybe I will design some more problems for the Nikilam method. So I think I don't think any these are all clear. This Nikilam and Trijagabham, Uddha Trijagabham. Then I'm starting today with division in Nikilam method. The basic purpose of division is to find quotient and remainder. We are by division we are not going up to the decimal part. That will be covered later in maybe tomorrow or something like that. So Nikilam method, actually this only aimed at finding the quotient and remainder for a division. The in Nikilam method, result of deficiency of the divisor from the nearest power of 10 is worked with, like division by 9. Okay, excuse me. Division by 9. So 9 actually is the nearest 10's power is 10 only. 10 only. So we can write here this. I write, and this how much is division? 1. So this line we put, it is a part of the quotient and remainder part. We divide this line with the quotient side and remainder side. So if 34, suppose I'm to get the result of this quotient and remainder when 34 is divided by 9. So when 34 is divided by 10, the nearest 10 of 10's power, 4 will become my remainder and 3 will become my quotient, isn't it? So that way, so I divide this line I put in such a situation. Now, because 9, it is not 10, it's 9 only. So in each of these 10's digit, there will be 1 extra. So that extra is put here. So this will contribute to my remainder. So that is, now my quotient remains as 3, but my remainder adds to 7. Is it clear? So you don't have to. This is the background logic I only explained to you. But actually, while doing so, you don't have to consider. You simply put these 3 here. That's all. You get the quotient and remainder. 3 here and add and then. So I'm dividing 61 by 9. Again, 6 I'm putting here. So 6 becomes my quotient and 7 becomes my remainder. So 123 divided by 9. This 1 I put here. 2 plus 1, 3. 3 I put here. So 2 plus 1, this 2 plus 1 becomes 3. And the 3, this 3 I'm putting here. And then finally 3 plus 3 is 6. and 12 plus 13, 12 plus 1 is 13. So 13 will be my quotient and 6 is remainder. Is this procedure clear? Here also 253 divided by 9. So 2 I put here, 5 plus 2, 7, 7 I put here, and then 3 plus 7 is 10. But 10 cannot be remainder in while dividing by 9. So again, with 10 also we do the operation like this. 1. So this contributes to 1 and this contributes to 1 again. So it becomes 28 my quotient and 1 is remainder. First you will understand this procedure. Where to put my dividing line? Because it is 10. 1 0 is there. This also you can do. Always don't have to consider dividing and so on. So how many zeros are there? Nearest base is 10. How many zeros are there? Only 1 0. So from the left with 1, leaving 1, I put this line. This becomes a dividing line between quotient and remainder. Now here 34 I'm getting divided by 9. So 3 I put here. This becomes the result. 61 divided, so 6 I put here. Here also this 1 is put here. 2 plus 1 is 3. 3 I put here and add up all them, quotient and remainder. Here I put 2 here. 2 plus 5. 2 plus, 5 plus 2 is 7. 7 plus 3 is 10. Again with 10, this 1 comes here and 1 comes here. This one. So 28 and 1. I come to higher. Yes.
Excuse me, sir.
Yes.
Sir, you have written 1 below 0 and below 27 you have written 1.
Basically, actually, it comes with, because actually it separate. It is being done separately. Actually,
You are writing the same one on both sides.
no, actually, I think I'll tell you because because see, actually, you can do by simply by minus also. 10 minus 9 is equal to 1. Okay. And one is so 1 quotient and 1 remainder. That I know, no? So earlier we had 27 as quotient and 10 becomes my remainder. So 27 was my quotient and 10 was my remainder. But 10 remainder is impossible in case of dividing by 9. So it will contribute to one more number of 9. So that will be 28.
Oh.
28 will be my quotient and 1 will become my remainder. That is the idea. So
it is clear.
Yes. So this 1 is put here. Basically, I am doing here actually. 10 minus 9 is 1. So this and basically 9 1 into 9 plus 1. So 1 into 9 plus 1 is 10. Okay. 10 is actually 1 into 9 plus 1. So 1 is quotient and 1 is remainder. So that 1 gets added to this one. So now we go to higher one. This was number was 12312, 5-digit number. So I'm dividing by 9. What you do? This 1 put here. 2 plus 1 is 3. Again, 2 plus 1 is 3. 3 plus 3 is 6. 6 plus 1 is 7. Okay. Then 2 plus 7 is 9. 1 plus 6 is this one. 3 plus 3 is 6. This one. 1, 3, 6, 7. And again, 9 is my remainder. 9 remainder cannot be there. So it becomes 0 remainder with 1 more contributing towards quotient side. 1, 3, 6, 8 and 0. So 1, 3, 6, 7, 1, 3, 6, 7 into 10 plus 9 is same as 1, 3, 6, 8 into 1, 3, 6, 8 into 10. So that is the idea. No, I'm sorry. 1367 into 9 plus 9 is same as 1368 into 9. So basically it's 1368 plus into 9. If I do, it will 12312. Okay. So 1367 into 9 plus 9 is same as 1368 into 9 plus 0. Okay. So this particular thing I'm dividing 1200212. 7-digit number, I multiply, dividing with 9. So what is the quotient? What is the remainder? So 1 into 1 becomes down here. 2 plus 1 is 3. 3 plus 0 is 3. 3 plus 0 is 3 again. And 3 plus 2 is 5. Okay. 5 plus 1 is 6. So this becomes my 8. See, you consider how much time it will take if we do like this. The conventional division method, if I do, I've learned like this, maybe that in your state, so you have to 9 into 1 is 9. Again, that always doing tables of 9, there is 9 to 9, 3, 27. You see, remember you understand, no? How much big it will be? You have to always mentally multiply with 9 tables of 9. You have to fit here, fitting. It will be very at least 2-3 lines like this. Okay. Here in one line you get the answer. Quotient and remainder. One line method. Sometimes they are called one line methods. Huh?
Sir, whatever may be the dividend, like we are dividing 9 by any number of digits like 10, 20, 30 digits, it's possible?
It will become bigger actually. It may complicate sometimes.
Okay.
But as I comparing here in this 7-digit number, for example, given the 7-digit number, some zeros, of course, it becomes more transparent. But had it been not zeros, then also it had been only bigger numbers, but it would not have much problem actually. It could have been easy, because actually basically what I'm doing, the idea is, the division basically is repeated subtraction. Here, by this method, we are doing that repeated subtraction. But here, I am doing it different way. I am considering it that I am dividing it to nearest tens. So 1200212. If I divide by 10, so it becomes 2 becomes my remainder, and this 120021 becomes my quotient. But I'm not dividing by 9. I'm not dividing by 10. I'm dividing by 9. So in each of these hundreds, tens, hundreds, thousands, 10,000, and so on, it will be 1. This 1 is the deficiency from the nearest 10. So 1 will be extra. So this 1 will contribute 1. Then in the this 10 to the power 7. Sorry, 10 to the, this is the 10 to the power 6 one digit. In the 10 to the 6 means your 10 lakhs means in 10 lakh, 1 lakh will be contributed. Again, becomes the 3 lakhs. In 3 lakhs, 3 will be contributed in the 10,000. In the 10,000 again, this 3 we will contribute towards 1,000, and that way actually. In each of these sections, it will contribute. That contributions I'm adding. Idea is that those contributions basically from the earlier quotient, those contribution coming from those 10, each hundreds, 1,000, 10,000, lakhs, and so on, we are this contribution from the extra 9, extra 1 that is coming out because of the deficiency, I'm adding them. So here, first division is done in the first go. Here, when I put a line, my division is complete. What I'm doing, those deficiency, contribution from the deficiency I'm adding. So this is basically subtracting only repeated subtraction is done in the first go, and then I'm adding only this adding. So therefore, it is addition. So here it was continuously with subtraction in this method, conventional method, but here I am doing by addition because the division is done in the first go. Here also I do continue it like this. So here also deficiency is 1. So 9, this 9 into 1, the 1 into 1 becomes this 1. This 1 plus 0 is again 1, and 1 plus 1 is 2. 2 plus 1 is 3. This 3 plus 6 is 9. This 9 plus 4 is 13. With 22. 22 again I do 9 like this, and then becomes 2 and 4. So this 2 is added to this one. So this plus 2. This is added. This basically this 2 is added here. So this becomes my quotient, and this becomes my remainder. Okay.
Can the
Sir,
same method be applied for 2 digits also? For example, 12 or 14?
Not yes, 12 will be covering in the next part, this after Nikilam. See, coming to the 2-digit, instead of 9, you are telling some other digit. So first I started with single digit, then I'll develop to 2. So this part is complete.
Okay.
Yes, sir. Sir, does computer does in this way or like other way, like what we are doing in the traditional way? How the computer calculator does? I have a question.
As I told, the traditional method constantly, it is a repeated division is nothing but repeated subtraction. We are subtracting in each of these powers of 10 when higher place values. First started with this, but this actually will involve always the tables of 9. Tables of 9 will be required, but here only tables of 1. Because 9 is deficient from 10 is 1 only. So tables of 1, because we are not seeing, because we are multiplying, we are just copying it, means multiplying by 1. So this is just a first I divide by 10. So find it that, and then we find the contribution coming from this 1 in each of these locations, each of the place values. Then finally add it. So it becomes the modified this quotient and remainder. Okay, that is the idea. So if I give more example, it will be easier. So
Sir,
division by.
I have only one doubt, sir. Like we have a computer, laptop, and other things. Like maybe I'm not sure how it works in the backend programming. Does they use this method, or nobody have invented this method? Like they have not made this method in the computer. Computer, we have a calculator, right? It does some operations.
Calculator actually uses multiplication methods in the background. These are done in assembly language. As I told, in the assembly language also, if a multiplication method is used, conventional method, it will be, if we use this Ujjati Jagabham, it will be actually more easy in the circuitry compared to the conventional method. In conventional method, this algebra, actually is more time consuming compared to this algebra. This is Ujjati Jagabham algebra. So in the background of any calculator, some multiplication method is used. So this is actually more time.
No. What my question was, like currently we have a Vedic mathematics. Okay, we have a computer. In the computer, we have a microprocessor. Microprocessor has its own language. We call it assembly and machine language. Okay, like they work on the zeros and ones, like zeros and ones, binary and like decimal code of system. Now I have only one question. In the world, anybody have used this Vedic method in the back end of programming of computer?
Now circuits are getting designed with this Ujjati Jagabham method. They found it. Actually, this is also being taught in school. Ujjati Jagabham in a different form. It is being taught in schools also. Like this one, here like this. You must have seen sometimes. It do like this. Like this one. Oh, I'm sorry. I did in opposite. It is like this. This one.
It will go in top and it will come in bottom. Yeah.
Huh? this way, sorry, not this one. So if we have said four-digit numbers are there, okay. So this one actually, first you have to multiply it by this, and then in each of these, I mean, there will be like this. So actually, it basically, I'll give you the diagram sometimes, and this is basically, you will find that this becomes, and when you added this is just adding up. This adding up each of the place values. So it is there. It is getting used in schools now, and it is found that this is easier than the conventional method. Now,
So
some
for
schools they are teaching already this. They're teaching up a method in this format. They are teaching it.
so when they are using animation, so the backend algorithm, do they use something like this?
Yeah, actually, this is it is found to be less in procedures. Numbers of procedures are less. Number of assembly basic operation is less here. So obviously it will consume less time. Delay will be less, and it will consume less power also. So that way it is being thought. Circuits are getting designed this way. Yes.
So you mean to say the generations, what we are saying, like the 11th generation, 12th, 13th generation. So these generations are already incorporated.
Always, people always use the best way to calculate in the background. So they take help of Vedic mathematics. Maybe anything. There are other departments. In the Vedic mathematics, there are departments, or they take help of all these things. Yeah.
It reduces the load of the RAM, I guess. This method.
Yeah, there is a load of RAM, obviously. Okay, unnecessarily
operations will be done quickly, so the microprocessor speed will increase, like the 8084 processor we are using now, microprocessor. Maybe the speeds are increasing. Yes, sir, I could get. Thank you.
Yeah. So now come to this one, 876. So 8 actually deficiency is 2. So, like say for example, 23 divided by 4. Now, for each of these tens digit, there will be 2 contribution. So 2 into 2 is 4. 2 into 2 is 4, and then we 4 plus 7. So if I divide by 23 by 8, 7 becomes my remainder and 2 becomes my quotient. 2 into 8 plus 7 is 23. So here 31 divided by 8. How? This 2 into 3 is 6. So 6 plus 1 is 7. So 3 becomes my quotient and 7 becomes my remainder. For 7, the deficiency from the nearest 10 is 3. So 1 into 3 is 3. So 2 plus 3, 3 plus 2 is 5. Then it can becomes 20 by 7. So 2 into 3 is 6. So 6 becomes my remainder and 2 becomes my quotient. And then this 11 divided by 6, 4 into 1 is 4, 1 and 5. So 234 divided by 8. 2 into 4, 2 into 2 is 4. 3 plus 4 is 7. 7 plus 7 into 2 is 14. 18 becomes my remainder and 27 by quotient. So basically 18 becomes again, you can do it this way also, or you can directly, sometimes you do by your own common sense or conventional method, whatever it is. 18 remainder means 2 more numbers of 8 are there. So 27 quotient becomes 29 quotient, and only 18 remainder remains as 2 remainders. 345 divided by 8. So 2 into 3 is 6. 6 plus 4 is 2. 6 plus 4 is 10. Into 2 is 20. So 25 becomes my quotient. Remainder. 25 becomes my remainder. And 34 plus 6, 40 becomes my quotient. But as you know, the 25, again, there will be divided into the 3 into 8 plus 1. So 43 becomes my quotient and 1 becomes my remainder. All other is also this, like this also you can do. No problem. Always don't have to do. Sometimes certain things you can do by 22 is 4. Of course, this comes another step. This 2 and 9, and again this 2 and 9 becomes 2 quotient and 1 remainder becomes 3 quotient and 1 remainder. 2 and 9 remainder will become 3 quotient 1 remainder. So finally it comes to this. So that way, as you see, it is more away from the. Therefore, I've given the very small example. Even away from the 10 nearest base, it becomes more complicated. So this method is best suited for which is nearest to the base. Now I come to 2 digits. 2 digits, so 89, and now the divisor is 89. I'm dividing 111 by 89. So 89 is now nearest tens power is 100. So how much is deficient Nikilam Navatas Charamodasta? This becomes 89 becomes 11. Nikilam Navatas Charamodasta. So this 1 into 11 is 11. So 1 becomes my quotient and 89 to 22 becomes my remainder. So you compare this how this is done. So if I do like this with 89, okay, 89 is a small. This one is small number. Suppose here also, suppose here, say 2, 3, 4, 5, and I am dividing by 789. Okay, so this will be very conventional method. Will be this one and then multiply this thing. It will be very long, very cumbersome. Instead of that, what I'm doing, I am considering the deficiency. So if there are 2 zeros here nearest 10, so you put put 2 places for these 2 places are for this is not vinculum. Just 2 places for remainder. So I put the line here, and then 1 into 89, 1 into 11 becomes 11, and 1 becomes my quotient, then 22 becomes my remainder. Similarly, 87, so it is 13. So 2 into 13 is 26, and 26, add it here. So 2 becomes my quotient and 48 remainder. So 88, it is 12. 100 minus 88 is 12. So 3 into 12 is 36. 69 my quotient, and 3 becomes my, sorry, 69 is remainder, and 3 becomes my quotient. Similarly, 1, 2, 3, 4 divided by 888. So this nearest base is 1000, and also this as there are 3 zeros, I put 3 left 3 I put here. Okay, only 2 are put here, 3 are put here in the remainder and quotient and remainder division line. Then 112, 1 into 112 is 112, and then 1 becomes my quotient and 346 remainder. Division by 2 or more digits requiring single processing. Just single processing. These two, the simple examples are to understand the procedure. Now here 789, Nikilam Navatas Charamagdasta gives here 211. 211. Divide, subtracting from 9 and subtracting from 10. 211. This 2 into 211 is 422. 767 my quotient. Oh, sorry, 767 my remainder, and 2 becomes my quotient. Is it clear? Is it easier than the conventional method?
Yeah, definitely.
Because you have to get the tables of 7, 8, 9, multiply by how much it is coming, whether it is coming 2, coming 3. Don't have to consider here. You in the first, whenever you are putting this line, your division is complete. Only this deficiency, you have to add up this in each of the 1000. Contribution will be this 211. So there are 2 numbers of thousands are there. The contribution of 211 in this 2000 will be 422. Multiplied. This is multiplied by 2. So this now the contribution from this, because of the remainder, this contribution at the remainder we add. There can be in the next examples we'll see that contribution will come from quotient side also.
Sir, if we have a number like 1, 2, 3, 4, 5, 6, 7, 8, 9, and if you want to divide 8, 9, 7, this method will be applicable for the bigger number.
Provided this divisor is near about 8 powers of 10, a power of 10. Okay. Divisor should be near about power of 10, either slightly below or above, but it will be near about 10's power. Otherwise, this procedure will not be there. So this is called Nikilam method actually. So here, division by 2 or more digits requiring multiple processing. So here, this 4-digit number now, 1111 is getting divided by 89. So 89 Nikilam now is 11. And then the 1 into 11 is 11. So 1 here and 1 here. Mind it, it is coming from this
21.
one below this first digit. Now 1 plus 1 is 2, and 2 into 11 is 22. It comes to the remainder side fully. Now here we actually already this 1 is written, but actually mind it, its contribution is 10. Okay, so that way it is added. So you don't have to always write this 0. 1 plus 2 is 3, and 1 plus 1 plus 2 is 4, and this 1 plus 1, 2, and 1. So 12 becomes my quotient, and 43 becomes my remainder. 21456 divided by 789. So Nikilam of the Star gives 211. So 9 minus 7, 9 minus 8, and 10 minus 9. So 2 into 211 is 422, 4 this side and 22 this side. And again, 4 plus 1 is 5, and 5 into this one, and fully comes to, it is not that 1 will come towards remainder, quotient side. Fully it is remainder side, 1055. This is actually, basically it is, you mind it, this is actually 220 format. So that you have to consider that way. Although you do not write these zeros, but actually while adding, we consider that. Not that you 1 is added to this one. 1 will be added to this digit. So similarly here, 6 plus 5. So you totally you add these 3 numbers and becomes 700, 1731, 25 and 1731. It requires multiple processing. This is one processing, then another processing will come. 1731, again I do it, this 789, this 211, and becomes 943, 942, and becomes actually, you simply 789, 987, 942 minus 789 becomes how much? Actually, because the numbers of digits are same, this method cannot be done. So simply you subtract. So it is 153. So again, so 1 and 1 quotient and 942 remainder becomes 2 quotient and 153 remainder. So this 2 gets added to this, earlier it was this 25. So 25 plus 2 becomes 27, and this becomes 153. This is my multiple processing. Here also I find another example. 121,456 divided by 789. So 211 becomes my Nikilam Navata Charmadastra. We'll work with 211. Because as I told, the division is complete by this. Division is done. Now I'm adding this contribution coming from this deficiency. So it is contributing towards both towards quotient side and to remainder side. So 211 into 1 becomes 21 here, and 1 becomes here. 2 plus 2 is 4. 4 into this becomes 844. 1 plus 1 plus 2 is 8. 1 plus 1 plus 8 is 10. This becomes 2110. And mind it, actually it is actually invisible zeros are there, because actually this is, I'm adding, while adding, I'm basically adding 456 plus 100 plus 440, and then this one becomes 3106. And this 121 plus 21 plus 8 is 150. But 3106 again, when I'm dividing, this becomes contributing to 739. So this 3 gets added to this one and becomes 153 and 739. You compare with the conventional method, there will be a lot of processing has to be done. Here only 2 processings. In each of the processing there are few lines, but still compare. If you compare with that, you will find that, isn't it? It will be easier. It is looking easier.
Yeah, sir. Yeah, sir. But like in the calculator, when you do now, we'll get some point digits. Okay, like 22 by 7 will give 3.14151316x7. So can we get in that way? Here it's not possible, right? Like only we'll get some reminder, and that reminder cannot be found up to a decimal value. I mean
No,
to say like
we are not going to a decimal point here. Only quotient and remainder.
Like that coefficient again, reminder will be again lesser than the coefficient, then it will stop. This algorithm will stop, right?
Yeah. Yes, of course. Remainder means what? Remainder should be always less than divisor. Otherwise, means some more contribution has to be taken out from that one. Now 2, 3, 1, 4, 5, 6 is again 211, and then 2 into this one is 4, 2, 2. 3 plus 4 plus 1 is 8, and if I get the this is actually sorry. This I'm sorry. Actually, this is written wrongly. I should have done it first. Here, actually, it is 2 plus this becomes 422. This 3 plus 4 is 7. This 7, and this when I multiply by this by 7, it becomes 1477. There is no place, so I've written. Actually, it is writings is the same thing. Writing this, but 14 is actually below this. Remind it. Whole 14 is below this while calculating. While finally adding it doesn't matter. But here, when I go to next one, so this becomes 14 plus 2 plus 1 is 17. 17 into 211 is 3587. 17 into this. 17 into 211 is 3587. So this actually we add. Okay. So there are invisible zeros as I told. If we add all these numbers, it becomes 5013 and 287. Here you can add straight away add. Because 14 if I add with 2 and 1, it becomes 17. As 7 you have to put again. Anyway, I have to put it as a carry. That carry I can write directly. But while doing the processing, in this particular processing, you have to consider it. It is below for this one. Whole thing is below. Now 5013 again 211, 1055 and 1068 and again 1068. So there were 3 processings were required here. So as I will see that when it becomes more and more away from the tens power, then the processing will giving the problem, processing can be more. Here I next one I have shown that longer complication. Take for example this number divided by 654. It requires actually 5 processing. I've shown here. So therefore, see here you do this one 300. Nikhil now the is 346 because it's so big already. So obviously this will become this one. 3 into 3 is 3 into this one becomes 1038. Basically here again. This actually is this one. 10 is here. 10 plus is 10 plus 4 is 14 and 14 into this becomes 4844. So again, that is quite complicated. It looks like that. If we do it right in the sparse method, so this becomes finally this one. So I didn't go into the details because I have shown that. I'll show you that how getting away from the tens power becomes complicated. Here again you do like this. It comes to this 22. Then again we come to this 5411. This again becomes this one quotient and remainder. Again you do like then finally this becomes, and then you add up all this. So 492 here, 22 here, 5 here, and 2 here. But 2 again it was actually 833. By simply subtraction, I came to 3 and 179. So it becomes 3 actually. So this plus this 3, basically 2 plus 1, the 2, 3, and becomes finally 522. So basic mathematics is state division for the above problem. This was state division, basic mathematics, or you can do by conventional method. So here, see, conventional method is also a method. Basic mathematics, learning basic mathematics doesn't mean that you you forget the conventional method or take them in the low footing. No, not that. Depending upon what I mean to say, depending upon the problem, given problem, you can apply either the conventional method or any of these basic methods. You have learned only alternative methods. The best method you can apply. That is the idea of the basic mathematics, is to get that best algebra and best method, best procedure given the problem. Is it clear? Now, so when it comes to like this, you don't have to use basic mathematics. Either you use conventional method, or there is in the second level course, the state division will be taught. So you can do that. Any question from this method? Then I can go to the next one. Or first discuss me next one. Which is actually this method only there is a sub-base technique is there. Again, there comes to sub-base. So dividing by 23. Now I find that 23 into 4 becomes my 92, which is actually near to a power of 10. So I forget about 23 for the time being. Divide by 92. So 1011 was there. 1011. So 8 was my nickel or 8 is the deficiency from 100. 0 and 8, it becomes 10 and 91. When I'm dividing 1011 by 92, 10 becomes my quotient and 91 remainder. But 91 was a remainder for 92, but it cannot be a remainder for 23. So in the inside 91, there is another 3 numbers of 23 are there. So it becomes, in 91 becomes 3 and 22. So 91 is equal to 3 and 22. 3 quotient and 22 remainder. So now, when something is getting divided by 92, it leaves 10 as a quotient. But same thing when I divide by 23, there will be 4 times more. So multiply by 4. So 40 becomes my quotient coming from there, and 91 remainder. But again, 91 is equal to 322. So it becomes added here and becomes 4320. Please try to understand this one.
I think time is up, Mukherjee sir.
Yeah.
We'll go for Pradhana.
Yeah.
Okay. Thank you so much. Sundaraji, please.
स्वस्ति प्रजाभ्यां परिपालयन्तां न्यायेन मार्गेण महीं महिषाः गोब्राह्मणेभ्यः शुभमस्तु नित्यं लोकाः समस्ताः सुखिनो भवन्तु काले वर्षतु पर्जन्यः पृथिवी सस्यशालिनी देशोऽयं क्षोभरहितो ब्राह्मणाः सन्तु निर्भयाः अपुत्राः पुत्रिणः सन्तु पुत्रिणः सन्तु पुत्रिणः अथना सधना सन्तु जीवन्तु सरदां शतं सत्यं वद धर्मं चर स्वाध्यायान् मा प्रमदः सर्वे भवन्तु सुखिनः सर्वे सन्तु निरामयाः सर्वे भद्राणि पश्यन्तु मा कश्चित् दुःखभाग् भवेत् ॐ शान्ति शान्ति शान्तिः ॐ पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते ॐ शान्ति शान्ति शान्तिः सर्वे जनाः सुखिनो भवन्तु स्वस्ति
ధన్యవాదములండి. Thank you so much. Now we'll go for Janaganamana. जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल वंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाही तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे जय हिंद.
जय हिंद. सर्वेभ्यो धन्यवाद.
And somebody raise the hand, JBSM Lakshmi garu. You want to ask any question? Lakshmi garu, you want to ask any question?
అవునండి, ఎస్ అండి. I want to ask us, it's not, I would like to, I have a small doubt. With this division method and any of these methods, the Vedic methods, is it okay to be used directly with small, right from childhood? Or is it necessary to first understand conventional method and go to this?
Goutham ji, are you there?
Because you said multiplication tables are not needed for this. So is it okay if they directly go to this multiplication type of solving theory?
Do you get me? Yeah. Do you hear me?
Yeah.
Okay. Now, actually, I'll tell you this one. Conventional method, we learned conventional method because it looks more general. Don't have any power of the distinction. Power of is not required. Mechanically applying that thing to every possible problem.
Yes.
So that is okay. That is one of the method. But why should we stick to one particular method? That is my idea. When, say, for example, when you give this number, this one, I compared this thing. No.
Yes.
When
but
this
then you mean to say that they have to learn conventional method first and then go to this?
No, you can go side by side.
Can go side by side. We cannot get away with the conventional method totally.
No need. That is one of the method.
Yes, yes, okay.
One of the
So
method is conventional method.
this
So,
should be
there
used
is
as an
nothing wrong in
alternative.
there is nothing wrong in learning conventional method.
Ah,
Only thing is that when you get a problem like this, for example, problem like this, why unnecessarily to multiply 7 by 6, 7 to 7, 7 all these things, 8 into these big, very big numbers like this. You see that these are both are very close to a particular
yes.
base, and you do this one is so simple, directly you get the answer directly. So what is the wrong in this? You tell me.
No,
Learning what was wrong in learning this method in school level? Was there
this
anything wrong?
method is very good, but because conventional method is very long process of division and multiplication,
Yeah.
can they avoid totally that and come
No,
to?
no, no,
It's
not. You don't
possible.
have to avoid. You don't have to avoid because
It cannot be avoided.
no, it cannot be avoided because given the setup problem, this is here very special case. This is near a base.
Okay.
Near a base. Suppose had it been much away from the base, this itself would have been very big. So again, handling that will be bigger. I mean, complicated. So we have to always say. Also, you have to learn this Uddhachet Jagapam. Nowadays in schools, these are getting actually taught. This method, it is getting actually taught like this. I tell you how it is being taught.
Because I am in that
See,
field.
I'll tell you how it is being taught. I found some current in the students. Suppose this is like 43. Okay. And this one is 25. They do like this, and then first they divide like this. I mean, 2 by 2 only I'm showing. Okay. Okay. Now, this one is 15. So it will be divided like this. So 3 into 5 is 15. So 15, 1 will they'll be right here and 5 here. Okay. 3 into 2 is 6. So 6 is here and 0 is. So again, 4 into 2 is 8. 0 is here, 8 and 8. And 4 into 5 is 20. So 2 here and 0 here.
Okay.
So now they added here 5. It becomes 5 here. 6 plus 1 is 7 here. 8 plus 2 is 10. 0 here and 1 is for carry. So this 1 plus 0 is carry 1. So 105. That way that they are doing. They are basically learning this.
Yes.
Some of them they called it matrix method, or to get you the name, not matrix actually. Some kind of name is there. There is a name of this method is there, but actually basically nothing but Uddhati Jagapam.
Okay.
And it is found, as I told, it is found more efficient in computer. And nowadays, suppose not only in multiplication, suppose something is displayed, even these points are displayed. Whatever you are seeing on the screen, those points are displayed by using a lot of calculation. When you are looking at the mobile, that mobile, if a point and black dot or a white dot is displayed, or a colored dot is displayed on your particular location of your screen, mobile screen. So that requires a lot of multiplication. In the multiplication method is there.
Okay.
So in each of considering trillions of divisions, trillions of devices that there are throughout the world, and inside that, always there are trillions of these multiplications are going on. So in each of the multiplication, there is a saving of power, saving milliwatt. So if you add up all these things, it will come to a huge power saving.
Okay.
When you use a proper method like this, compared to conventional multiplication.
Okay.
So that is the idea. This one paper was written on this, that how using, actually they are already started using. All the circuitry now are being designed using Uddhati Jagabham method. Okay. Although they are not teaching in school, but they are using some schools, as I told, some schools have started teaching, private schools, not government schools.
Yeah.
So gradually it will come. My thing is that when basic mathematics people will learn, they will learn all things parallelly and found that and use it the best one to use.
Okay. So Vedic mathematics is taught as a separate thing, not along with mathematics in school. That's what I'm saying.
It should not be started as separate. It should be done
Along with the,
yes.
So parallelly along with that.
Exactly.
Okay.
All these methods should be parallelly can be taught.
But still, the multiplication tables make a
multiple tables
major
should
role.
always, it is good to have multiple tables should be required. But as you told that using vinculum, it should not be required. But doesn't mean that you should not learn multiplication tables or 8, 9, and so on.
Okay.
By using vinculum, your multiplication requirement would be up to 5 into 5 table. But that doesn't mean you do not learn it. You do not अनपढ़ रह जाने के कोई वो नहीं है ना माने you should not be deficient in any of these things. Never not meant to make anybody deficient in or anything. There will be more capabilities are added. Not anything is subtracted from here.
Okay.
Thank you
so much. Thank you so much. I had this doubt because you said this is a simpler method. So for children, it can be everything can be all those tensions can be.
I say that we are deprived. We were deprived in our childhood, but also some children are getting deprived of these nice methods.
Easier methods.
Easier methods to learn actually.
So one step division will always be easier for them than the long process.
Tomorrow I will start with this one. Which is earlier it was or below base. This was below base. Now above base, what to do? Something is to be divided by 112 and 1, 1, 2, 3. So tomorrow we will start with this one.
Okay. Thank you so much. Thank you so much.
Okay, Gautam ji, thank you so much. We'll close now.